Welcome to Easy Math TV. After working really hard in the previous video to create a probability distribution table for any kind of binomial experiment or binomial observations, we had to end the video pretty quickly. So we're just taking up where we left off. Notice our cumulative probability down here is equal to 1. We added up all of the probabilities in column F, and that number is equal to 1. So these are indeed all of the individual outcomes for when we are in our free throw situation. So let's actually go over here. Our goal for this video is we're going to answer 3 application questions, how to use our binomial probabilities to answer 3 application type questions. And the first one is the probability of getting between 4 and 6 free throw shots out of 11. Okay, so that number there, by the way, needs to be fixed because it's different. Let's go ahead and figure that out. So we need the numbers for x equals 4, x equals 5, or x equals 6, because that's anywhere between 4 and 6 are the values of x that we are interested in. So I'm just going to highlight those real quick. Let's highlight those numbers that we want. So across from 4, 5, and 6, we have 0.227, 0.230, and 0.166. If I grab a calculator real quick, and let's go ahead and add those numbers up. 0.227, did I tell you? Yes, plus 0.230 plus 0.166 equals, and it looks like it's 0.623. So 0.623, or if we put it in percentage terms, it's 62.3% of the time. 62.3% of the time, the number of free throws that this player will make is either 4, 5, or 6. So that will happen that percentage of time. Now that number can inform decisions like, what do we expect to happen? It's a pretty good bet, since it's more than 50%. I would take that bet. I probably wouldn't bet $1,000 on it, but I would take that bet. Okay, let's look at the second question. The second question involves flipping a coin, and we're not being told here what the probability of success is. But since we are flipping a coin, the probability of success for heads versus tails is assumed to be 0.5. So if it's not being given to you in the problem, we want to assume that the probability of success is 50-50. So that's going to be 0.5. I'm going to update that up here in cell D1. So our probability needs to be updated. And we're also not flipping the coin 11 times, are we? We're flipping the coin 7 times. So n is equal to 7. So that means we need to do 2 things. We need to change the value of n in cell B1 to a 7. And we also need to update all of our frequencies, which is another reason why only the cells that I've colored in salmon are going to be changed by me. Everything else is going to change automatically, okay? So let's go over here to our Pascal's triangle and get our values for n equals 7. Copy, which is Control C or Command C, copy, and then over here we're going to paste values, right? So any of these outcomes that go below the range of values that we are allowed to have, don't apply, okay? So x could either be 0, 1, 2, 3, 4, 5, 6, or 7. It can't be higher than that because we're only flipping the coin 7 times, okay? So if you're only flipping the coin 7 times, you can't get greater than 7, all right? Which means that this is our complete probability distribution in this situation, because the number of attempts we're making, or the number of trials, is equal to 7. And you'll notice that the cumulative probability is back to being 1 again. But what are we interested in? We're interested in less than 3 heads. Less than 3 heads. So that is 0, 1, and 2, right? Or 2, I should say. So 0, 1, or 2 heads. And that's these 3 probability values. So it's not good enough to just say, oh, 0.164. No, that's not a cumulative probability. That is an individual probability. These are individual values that need to be added up. So I won't show it to you because we only have a limited amount of time in our video. So add those 3 numbers, okay? Get out a calculator right now and take 0.008 and add it to 0.055 and then add 0.164 and see what you get. And then come back. Did you get an answer of 0.227? That's what you should have gotten. Okay? 0.227, or 22.7% of the time. If you flip a coin 7 times, you will either get 0, 1, or 2 heads. Okay? That's our second, so we've answered that question. Now let's go to the third question. The third question involves diagnostic testing, and we're concerned about, we're measuring how many false positives a person might get. How many false positives a person might get. So if we look at this problem carefully, we want to know what the probability of incorrectly testing positive one time or once. So X is going to equal 1. And it says for the disease, if tested for the disease 7 times. So again, N is equal to 7. So the good news is we won't have to update our value of N. N is fine. Let's get rid of the highlighting over here. Get rid of that highlighting. And the frequencies are fine because those go with our value of N equals 7. So the only number we need to change is our probability of any false positive test. What is the probability of a false positive test? It's 0.11. So that's going to go in cell D1. All right. So again, we're only updating, we're only making sure that the correct numbers are in cell B1, cell D1, and then our frequencies in column C. Everything else gets calculated automatically, all right? If our final row is not complete for some reason, then you can just do fill downs in these other columns. Like, don't forget that in column B for Bravo, in column D for David, E and F, you can just click on that anchor in the corner and fill down if there's any of these numbers that are missing, okay? But we want to make sure that these blocks are filled so that we're good. And double check our cumulative probability down at the bottom is equal to 1, so we're good to go there. All right, so the false positive situation, what is the probability of 1 false positive? In other words, X is equal to 1. So I go there and I highlight that. And going across, there we go. It is 0.383. So when I go down here, I'm going to put 0.383 or 38.3% chance. 38.3% of the time, a person undergoing this particular diagnostic test, if they do this test 7 times, they repeat the test 7 times, there is a 38.3% chance that one of those 7 times will result in a false positive. And we know what that means. That means that you've tested positive for the disease, but you don't have it. So it's always important to follow up and get further testing so that you know for certain that you actually have the disease, even though you've tested positive for it. So that answers those 3 questions, and you'll see more questions, more types of questions that involve binomial trials. Binomial trials have to do with trials where there's 2 results, 2 outcomes, and we're measuring the number of positive outcomes, or number of successes in out of a certain number of trials. Okay, like, subscribe, comment down below, share these videos with other people if you think that they'll find them useful, and then we'll talk about, in the next video, we'll talk about finding the mean and the standard deviation for binomial distributions. Okay, see you in the next video.